The whole problem began when the chemists took over. In 1909, the Danish chemist Søren Peter Sørensen introduced the pH value as a measure of free hydrogen ions. The advantage of the pH value is that it represents the concentration of hydrogen ions on a log scale. Therefore, it covers a wide range of concentrations. The disadvantage is that it's not really intuitive. Now, what is the pH value and why is it important? Let's take a pH value of 7.4. As we said, this is a measure of the concentration of free hydrogen ions. So a pH value of 7.4 would equal a hydrogen ion concentration of 10 to the minus 7.4. I'm going to show you a comparison to the concentration of potassium ions a little later. So I would like to convert this number into something that's more comparable to the normal potassium concentration. So 10 to the minus 7.4 would equal to 4 times 10 to the minus 8. Now, you don't have to do the calculation yourself, just trust me on this. As you're probably aware of, that's nanomolar. Now let's compare that to the concentration of potassium, as I said previously. Now what's the normal potassium concentration? That's about 4 millimolar, right? 4 millimolar would equal to 4 times 10 to the minus 3. Now you can probably see why I converted the pH value above. Now what's the difference between 4 times 10 to the minus 3 and 4 times 10 to the minus 8? Well, that's a factor, or gradient, however you want to call it, of 10 to the 5th. So that means, in other words, that the concentration of hydrogen ions is 100,000 times lower than the concentration of potassium ions in the blood. The correct concentration of hydrogen ions in the body is key for life, and it's regulated in a very narrow range. And that range is between 44 and 36 nanomoles per liter. So if the concentration of hydrogen ions is below 36 nanomolar, then that means that the pH will rise above 7.44. This would be called alkalosis. On the other hand, if the concentration of free hydrogen ions is larger than 44 nanomoles per liter, this would mean that the pH value would fall below 7.36, which we would call acidosis. Acid-base disorders are classified into either metabolic or respiratory. So there's a metabolic acidosis and alkalosis, and there's a respiratory alkalosis and acidosis. These can occur isolated or combined. Now, why is it important to keep the concentration of free hydrogen ions in a very narrow range? Because they're very reactive, which means that they can bind to usually negatively charged proteins and thereby change their conformational structure, making them less functional. Let's take an example. The enzymatic capacity of lactate dehydrogenase, which is an enzyme that converts lactate to pyruvate, and vice versa, outside of physiological pH of 7.4 drops dramatically, both if the pH is too high and the pH is too low, as you can see on this curve. So as you can see, the enzymatic capacity of lactate dehydrogenase drops below 60% if the pH is below 7 or above 8. And the same holds true for other proteins and enzymes as well. Okay, so we said the body needs to maintain the pH in a very, very narrow range in order for the enzymes in the body to work. This capacity is really, really impressive, especially if you consider the amount of hydrogen ions produced in the body. The net acid production in the body is in the range of 100 millimoles per day. As we said before, the concentration of free hydrogen ions is in the range of 40 nanomoles. So the difference between the acid production of 100 millimole and the concentration of free hydrogen ions of 40 nanomole is in the range of 2 million. That's what the body has to accomplish each and every day. In order to maintain this huge gradient, the hydrogen ions need to be buffered and excreted from the body. The enzyme that catalyzes this reaction is called carboanhydrase. It catalyzes the reaction of free hydrogens with bicarbonate and its transformation into water, H2O, and carbon dioxide.